It might not. That's something we'll look into more later too. Okay. So all the graphing stuff. The only thing that I want to talk about before we're done are these things called one-sided derivatives. And believe it or not, you guys actually have done this a little bit too. So let's say I have a function that looks something like this. To know what's the derivative at 0. So if this is f of x, I want to know what is f prime of 0. Okay, not f of 0, f prime of 0. So what is the slope there? If I asked you for the slope anywhere else on this thing, you could do it. But why can't I answer this question at that point? So the slope of it, like at that point, like instantaneously changes, right? As I'm coming at it this way, what does it appear the slope needs to be? 0. But as soon as I get there, this line now. And the slope of this line is certainly not 0, right? The slope of this line looks to be, I don't know, like 1 or 2 or something like that. Okay? So at this point, it has no derivative. What it does have is a left-handed derivative and a right-handed derivative. There's one-sided derivatives. Okay? So what is the left-hand derivative at this point? 0, because right, it's coming down and then the slope is approaching 0. What is the right-handed derivative over here? Like 1 or 2 or whatever the slope of that line is, right? So okay, if the left-hand derivative and the right-hand derivative are not the same thing, then we say the derivative does not exist at that point. And so in this case, there would be no just regular derivative at that point. And this is something we're going to get into big time in the next section. When we talk about differentiability, remember I talked about determining if a function has a derivative or can we calculate a derivative or not at specific points. We're going to be investigating this quite a bit. These left and right-handed derivatives. Are they the same or not? So can we actually find a derivative there? And what we're going to find as part of that, notice how this function is not like smooth through this point. It makes kind of a little corner, okay, because the slope is doing one thing and then all of a sudden, boom, it's doing something else. Okay, having a corner on a derivative makes it non-differentiable at that point. Can't do the derivative there. So that's kind of the idea. So let's try this once. I'm going to come up over here where I've got some more room. And we'll calculate some one-sided derivatives. Okay. Okay, so let's say we've got f of x. It's defined in two pieces. Go with the same thing that we had here. So let's say it's x squared when x is less than or equal to 0, and it is x when x is greater than 0. So what we're going to do is, and we already said we kind of know what the answer is, right? The left-handed derivative is 0, the right-handed derivative is 1. Well, let's go prove it. We're going to do this whole limit as h goes to 0. We're going to actually calculate it and show that they come out different. So to do the left-handed derivative, we're going to do the limit as h goes to 0 from the right, though. I'm sorry, from the left, so that'd be a little minus, not a plus. Okay. So remember when we did the left and right-handed limits? We had to put the little plus or the little minus or whatever. Well, the derivative then follows that same idea. So it's the limit as h goes to 0 left of f of a plus h minus f of a all divided by h. Okay. Now this limit coming from the left-hand side simply indicates then which piece I need to go with. So from the left, which piece am I using? First one or second one? First one, right? This is when x is less than or equal to 0. That's everything to the left of 0, right? So I'm going to use that piece in this limit then to do the left-sided derivative. So that's going to be the limit as h approaches 0 from the left. F of a plus h squared minus f of a would be a squared divided by h. But what is a in this instance? 0. So we got the limit as h approaches 0 from the left of h squared minus 0 over h. So that's going to be h squared over h, which is just the limit as h goes to 0 of h, which is what? 0, right? Plug it in. So the left-handed derivative is 0, just like we said it was, right? Rachel, question? Because we're determining if f prime of 0 is, or what the left and the right-hand derivatives are at 0, at this spot right here. If I had done it like over here somewhere, maybe at 2, then I'd be using a 2 for a, but we're doing it at 0. Correct. Yeah, and that's important to note maybe. A is the x value. So this would be like prime of a is what we're doing here. In this case, then we're looking at f prime of 0. So a is 0 in this case. Yep. Okay, so that's the left. Doing the right, same, except we're using the other piece. The other side is 0, so it would be the limit as h approaches 0 from the right, so a little plus, of f of h minus f of a, all divided by h. And so in this case, I'm going to use just the function x. So it's the limit as h approaches 0 from the plus side. A plus h, so that would be just a plus h, minus f of a would be just a, divided by h. 0 again, so we end up with the limit as h approaches 0 from the right. And let's see, what do we got here? This is just going to be h over h, right? Which is the limit as h approaches 0 of just, well, 1, right? There's no h to plug into, so what's the answer? 1. Yeah, it just stays 1. Okay? So if I'm like giving you a problem, something like, okay, take this function up here, prove to me that the derivative does not exist at 0. This is what you would do. Okay, I'm going to show you that the left-handed derivative and the right-handed derivative come out to different values, so therefore that derivative can't exist at that point. And that's exactly what we just did. Okay, from the left we're getting 0, from the right we're getting 1. Derivative at 0 can't exist then. Okay, so it's doing all this limit business again. You just have to go one piece at a time and show that they come out to something different. The question might also ask you, show that the derivative does exist. So maybe even though it's in two pieces, maybe the slopes still end up coming out the same. So maybe it does connect nice and smooth and the derivative does exist there. So then you'd have to kind of go through the same thing, but then show that the two numbers are the same. Okay? So the idea with that. So just because you're going to see some of it, we'll get a lot more into this later, but I want to talk a little bit of notation stuff, and then I really will be done, I promise. I know we've done a lot today. There's a little history here that I have to let you guys know about. There are two mathematicians that were alive roughly the same time. Both claim to have, quote-unquote, invented calculus, but they were working completely independent of each other, and they had different ways of writing notations, and depending on what you do, how you're using a derivative, one notation is more accepted than the other. So Isaac Newton is the one, which we've already talked about. And then there's this French guy, Leibniz, who was also working on derivatives. And so we have Newton notation and we have Leibniz notation. But it all means the same thing, okay? So I just want to show you a whole bunch of symbols that all mean derivative, okay? So this is some Newton stuff. So f prime of x, you've already seen, that means derivative. You also might see it written just as f prime, without the of x. But it still means derivative. It's the same thing. Okay? Now, Leibniz, I kind of like his notation because it kind of shows you more of what exactly you're doing. His notation is dy over dx. And think about when we did all this instantaneous rate of change business, what were we really doing? Change in y over change in x, right? Now, dy and dx are these things called differentials, which we will also get into later. But in any event, do you see how that kind of shows a rate of change? It's a fraction, it's a ratio, which is really what you're doing when you're doing this kind of stuff. So he does it that way. Another way that he does his notation, depending on what you're doing, you might see it just simply written as d dx. Okay, so dy dx or d dx. Another way that he did it would be like df dx. So instead of talking about y and x, it's a function versus x. And then there's also this d dx of f of x. Okay, so you got your Newton ones here, and then your Leibniz, all of these types of things. But every single one of these is really just the derivative of a function. Okay? And your textbook, throughout this chapter, is just going to chuck these at you in random spots. Okay? Find f prime of x. Find dy dx. Find df dx. Find d dx. Find f prime. It's all the same thing. Find the derivative is what they're asking you to do. Okay? So, yeah, Newton stuff, Leibniz stuff, but all the same. All the same. So, okay.